Chapter 12, Video 3. This will be our last and final video, unless you watch the bonus multiple choice video for Chapter 12. This one is our chi-square test of independence. So this is the third and final type of chi-square test. This one is going to be more similar to a test of homogeneity than it will be for a goodness of fit test. So what exactly is a test of independence? Well, we're looking for an association, basically like a connection between two categorical variables, but only in one population. So remember, a goodness of fit problem was one categorical variable in one population. A test of homogeneity was looking at one categorical variable in multiple populations. And now a test of independence is looking at two categorical variables, but only in one population. So again, the one big difference between a test of homogeneity and a test of independence is how many categorical variables are we looking at versus how many populations are we considering. So it really boils down to how many random samples were taken. If there were two or more SRSs or random samples taken, this is going to be a test of homogeneity problem. If the problem says that they only took a single random sample, then this is going to be a test of independence problem. So the question we're going to explore in video 3 is your index finger or ring finger longer? It is not the same for everyone, actually. To investigate if there is a relationship or an association between gender and relative finger length, we selected a random sample, notice a random sample, one random sample of 460 U.S. high school students who completed a survey. The two-way table summarizes the results. So notice, just like in a test of homogeneity, we have a two-way table, which means when we do this problem with our calculator, we're going to use a matrix again. So, do these data provide convincing evidence of an association between gender and relative finger length? We're going to use an alpha level of 5%. All right, so again, we're looking for an association between two categorical variables. What are our two categorical variables? Finger length and gender. Who is our one population? All U.S. high school students. How did we know it was U.S. high school students? Well, look at your random sample. A random sample of 460 what? U.S. high school students. Who is our population? U.S. high school students. So our observed data. This is what we started with, and now we need to consider what are our expected counts. Here's the nice thing. It uses the same formula that we did a test of homogeneity, where it's row total times column total divided by the total. And we talked about some strategy in the last video where we said, you know what, we don't really need to figure out what all 6 of these numbers are, because really that smallest value is the main one we're looking for. Now, if you want to fill out all of them, I would make that recommendation, especially if you're taking the AP stats exam. I'd have to really go back and look and see on a rubric if you have to provide all of the expected counts or just show work for one expected count. I can't remember, but I would probably write down all of the expected counts if you're taking the AP stats exam. Now, how did we find which one was going to be the smallest expected count? Well, remember, we had to look at our row subtotals and find the smallest one, which would be this 86, and then look at our column subtotals and find the smallest one. Well, that would be 227. And so where those would intersect at, so this would be female and same length, then that would be our smallest expected count. So if we took 86 times 227 divided by a grand total of 460 people, the smallest expected count is 42.4. Now remember, all we really need to do is figure out one more expected count in this 3x2 table. So for instance, if I figured out how big that number was by using the same formula, then I can get 78.0 here. And then from there, I can really use the subtotals to help me figure out what all the rest of the values are. Because remember, 78, 42.4, and the third entry here all have to add up to be 227. So subtracting those, I can figure out that this third number has to be 106.6. And then when I subtract these row subtotals from the first column numbers, then I can figure out quite easily what those other expected counts are. So again, you can easily figure out what these expected counts are, especially if you have a small enough table to work with. All right, so what in general do the null and alternate hypotheses look like for a test of independence? So the null hypothesis is, just in general, there's no association between variable number 1 and variable number 2. So remember, the null hypothesis is the dull hypothesis. There's nothing special, nothing fancy going on here. So in general, no association. That sounds pretty boring. Versus alternatively, we want to show that there is an association between our two categorical variables in our one population of interest. So for our problem, the null hypothesis would be there's no association between gender and finger length. Now, if we want to, especially if you're taking the AP exam, you might want to also include in here in all U.S. high school students. So we can throw in our population of interest in there. Alternatively, we would say there is an association between gender and finger length in all U.S. high school students. The conditions, same as they were before. We got to have that random sample. And remember, for a test of independence, there's only one random sample. So it said a random sample of 460. Cool, proceed on. The independent condition, since there's only one random sample, that means there's only one population of interest. So we only have to check the independent condition one time. There's only one population, and that's all U.S. high school students. Can we assume that there are more than 4,600 U.S. high school students? Absolutely. Now, also consider if random assignment was used in the problem, then there's no need to check the independent condition. You may proceed on to the large counts condition. Are all the expected counts at least 5? Well, we already figured out the smallest expected count was 42.4. So we may proceed on from there. Now for the formula, if we want to do this by hand, and again, it's the same chi-square test statistic formula that we've used for all 3 now of our chi-square tests. So observed minus expected, square that difference, divide it by the expected, you get the individual chi-square value. So again, for my work, if I wanted to show abbreviated work, I kind of started with the top left, did observed minus expected squared over expected, plus ... went down all the way through to the bottom right corner of my list. Now, I showed what all, in this case, 6 individual chi-square contributions were here, and then I added them all up to get this 6.148. Now, if you were doing this by hand, you don't really need to show what all of these individual values are. But if there was a follow-up question and it said which one was the most off, then you've already got these set up to examine to go, whoa, this first one was the most off because it had the highest chi-square contribution out of the entire 6.148. Now, you can always just go, here's the formula at play, and then here's what the chi-square test statistic adds up to be altogether. Now, 6.148 was our chi-square test statistic. It's always greater than or equal to because our chi-square values are always positive and they're always going to shoot off to infinity. So we can start with that as our lower bound, always go up to infinity. For degrees of freedom, it's the same as what it was for a test of homogeneity. It's the number of rows minus 1 times the number of columns minus 1. And I left us with a very similar example of like what we did previously. And we're still going to have 3 rows and 2 columns. And so 3 minus 1 makes 2, and 2 minus 1 makes 1, and 2 times 1 gives us 2 degrees of freedom. Now my p-value comes out to be a little under 5%, 4.624%. Now if I wanted to use my calculator command instead, same exact way with a test of homogeneity. We need to go to our matrices. So press that second button, go to the inverse button to get up to that matrix, go over to edit, we'll select matrix A. Even if you already have numbers in matrix A, we're just going to rewrite over matrix A. And there's no need to clear it or delete the values in it. We're just automatically going to rewrite over this thing. Now, if you had already done this in your calculator for the video 2 problem that we did, you might already have a 3x2 matrix in here, and then you can really just write on top of your old numbers. If not, Remember, the first number represents the number of rows we need. The second number represents the number of columns we need. So again, we need a 3 by 2 matrix, and then I input in my values, my observed values. Remember, we don't have to mess with the expected counts because the calculator is going to do it for us automatically. So we press the Stat button, go over to tests. Again, we're going to use just the plain old chi-square test function here. We're not going to use the GOF. Observed, hopefully you still have this as matrix A. Expected, remember, by default, the calculator is going to do all that for us, so we don't have to mess with it. We just have to leave it as kind of the default matrix B. Now, the only time you would need to change this would be if you had your observed matrix B. Then you might have to change the expected matrix to be matrix C instead, or something else. So that's why I always recommend, let's just put the observed always in matrix A. And by default, let's leave the expected as matrix B. Going down to calculate, we get our chi-square test statistic with our p-value. Again, notice these are slightly different than what we got when we used the formula, just because of all the little rounding differences, and that is 100% fine. Notice we still get our 2 degrees of freedom that the calculator automatically figured out for us by doing the rows minus 1 times columns minus 1. Now, if you need to, you could go back at this point and look at your matrix B, and you can see what all of those expected counts are. And so if you needed to make a table, and again, I would recommend this more so if you're taking the AP Stats exam, you might want to have a little matrix or a little table somewhere listed with all of your expected counts. And you also need to label. If you write out all the expected counts, you need to make sure that you identify them as the expected counts. I will say, I remember grading a particular chi-square problem once upon a time on the AP Stats exam, and students would list out what the expected counts were, but they never identified them as the expected counts. And so we were told if they didn't label what their numbers represented, we as teachers were not allowed to assume what those numbers represented. And so we had to deduct points in that scenario. Now again, where are the contributions? Unfortunately, we don't have them. So if you need to figure out what the individual contributions are, you have to do them by hand using that observed minus expected squared over expected formula. And again, we figured out that the largest contributor was really that very first one there, which would represent what scenario? Now I got to go all the way back here. That was looking at female and their index fingers longer was the most off from what we expected to see, right? We saw 90 and we only expected to see 78. So we saw, 12 more than we expected. So again, that contributed the most to our chi-square test statistic. All right, now in the end, regardless of whatever p-value we came up with, if we just use the formula with our chi-square CDF, or if we use the actual chi-square test command in our calculator, notice our p-values are very close to each other. And in both of those situations, they are less than the alpha level of 5%. So we still get to reject the null hypothesis and conclude that we do have enough, we do have sufficient, we do have convincing evidence, we have statistically significant evidence at the alpha equals 0.05 level to conclude that there is in fact an association between finger length and gender. Now, I've got one for you to try. It says 2,426 healthy volunteers were randomly assigned to take a 0, 30, 60, or 90-second cold shower daily to see if it helped reduce sickness in people over a 90-day period. So again, here is our data. This is a slightly different size matrix than the ones we've been working with in the past 2 videos, so just make sure you realize that. And I want you to come up with the expected counts, the chi-square test statistic, the p-value, and the degrees of freedom, either by hand or you could use your calculator to help you figure out all those numbers. And we will go over that the next day in class. I just want to say thank you for this crazy journey of AP statistics, whether you're one of my students or you're not one of my students. I hope you learned a lot this year. I wish you the best of luck if you take the AP Stats exam soon. And if not, I'm sure you'll take a stats course maybe in college, or maybe you are in college and you really need to pass this class. But good luck to you. I wish you the best of luck. And if you ever need any help, or if you ever have any questions to ask, you can always leave me a question here on my YouTube channel or on any of my videos, and I will get back to you as soon as I possibly can.